cross-posting this to streaming. Oh, not that one. This one. Nope, not that. Oh, dear Lord. Streaming. Alright, so stream. We just found this cool PhD student, and he posted a very cool code, and it's on Pluto, so obviously we stand Pluto. And Pluto is a really, if you've ever seen a Jupyter notebook, boom. If you've ever seen a Jupyter notebook, right, this is Alejandro R. Ursua, fellow Mexican theoretical physicist, right? We're not there yet, but we're getting to it. So Alejandro has been kind enough to publish some of his codes onto the internet, and we found it late at night one Friday, and so we're willing to take it out for a spin and see how much we can just crank the performance, because performance is sweet, and performance tuning is an art, and we're gonna get there. So his code is this. It's got some cool math. I don't know the math yet. I haven't really bothered to check it out, but he's been kind enough to put a link here, and so I'm gonna put the link in chat so that you can follow along, or you can just check for his account. Let me just verify that I am indeed doing what I want to be doing, which is streaming to people and not just talking to myself. Brain RPG. Yeah, gotta get that mobile phone dual workflow. So, yeah, looks like it. Alright, and I'm looking at my chat. I can look at my chat. Alright, so there's a task. There's some special functions here, which are, if you've ever done physics, like past the half the degree, then you've run into these bad boys. And so they're just nasty functions that are quite expensive. But there's quite a few like Pythonisms here. We're going to try and correct them. So there's some images. I'm not going to worry about the images. I'm just going to try and speed bump this code all the way through. So what does this look like? This looks like, oh, my camera is absolutely bonkers. So let's try and fix that. Why is the camera so bonkers? I don't know. Camera is bonkers. Alright, that should do it. And we should try and send this to that other screen, and then from the other screen we will take it here, and then this one. Oh, I don't want that. I want this. Looks more acceptable. Why? And obviously this is the font for ants. So that, alright, we're good. We're good now. So let me check just one last time, make sure that I'm not doing anything silly and that people can actually see my screen. Let's see. Here, let's not do that. Oh, okay. So it seems you guys can't see the bottom of my screen. Maybe that's because I screwed up the, yeah, that's the stuff. fidgeting on the settings live. Awesome, awesome recipe for success. Alright, but people love seeing what I'm using, so I think that we're gonna delay this just a little bit. Or at least I love seeing what other people use, so I'm gonna make sure that other people can see. Oh yeah, look at that Vim. Oh dear Lord, why is it doing this? What? Why are you doing that? Just stretch normally. Oh Lord. Alright, screw it. We don't need the entire screen. So this is it. And yeah, let me just check what it is I'm doing. Yep. And then alright, so I don't need that. Alright, we're live. So, or at least we should be. Checking one last thing before we blast off, and then should be good. Yeah, that font should be good for people. Alright, so what do? We just copy this code, we put it in this terminal. Oop. It should be a bit bigger, so it's not font for ants. There we go. Font for ants is live. Alright, yeah, that looks a bit better. So we're going to do this one step at a time. So, wait. Yeah, let's try and do this. Hello? Yeah. Okay, so the first few things that we see wrong with this code that I just deleted before I started this stream. Oh, I have to use the hypergeometric functions. Where is that from? Oh, I might have to use that here. We'll see if I have it installed. Alright, doesn't matter. So the first thing that is a big no-no, and we're going to post this in the chat for people who don't know either, because it happens to everyone, and especially people who come from Python, they struggle with this. What they struggle with is reading the performance part. Performance tips manual Julia, right? So if you come from Python, you should literally just read this before you have to do any heavy numerical computation. At the very top of that bar, you can see that it says avoid global variables. So exactly what we're doing here, right? You declare an x as a local variable and then you use it somewhere within your functions. That's a bad thing to do for Julia. Julia's compiler is not magical, and it will absolutely bail if it cannot. So you won't get any cool optimizations because the compiler will just say, I don't know how to deal with global values. So it just quits. And so that's the first thing that we have to get rid of. And we get rid of that by declaring these as constants, right? These do not change during the rest of the code. It's good for us to benchmark with just these constants, and so we just declare it constant. That's fine for now. All right, what's next? They're going to use it. We're going to need this funky function. And so the next problem that we run into is that there's like some integer, like some type declarations in the function which you don't need. Like this hypergeometric function only works for integers, and it will bail. I'm going to assume it does, but I'm pretty certain that it does. It will just bail if you hand it like floats. So you don't need these type annotations. These are redundant. They don't help your code. Like they don't make your code any faster. They help you filter out for behavior later, but we're not dispatching on anything special. So we don't need it. You don't need it at all. Don't need it. So this code is going to look like a bunch of like funky functions, jhype, jhypef, and then populating some big arrays, right? So this, or maybe not big, but we'll see. So j is 2, then 2 by j is 16, and then dimension n plus 1 is 1, so 17. So these matrices are 17 by 17s of 64 floats, right? Big problem here. So we're going to get to that. One problem here is that we are using big numbers for some reason, although these are not necessarily these are not necessarily these are being fed to the gamma function. So maybe maybe we don't need big numbers here. Maybe we do, but maybe we don't. So we can get rid of the big numbers or factor those numbers before they get into the gammas. Maybe that could help. And then this 2 to the something float 64, this is funky. This is a funky type declaration. We're going to see how it works. So we're going to try it out on some inputs, right? And then there's the image, and so here you have something really cool, right? There's an image for this, and this is a matrix that looks like it's on the upper side of this. So this is called an upper triangular, and it looks like it's symmetrical on the anti-diagonal. Yeah. So maybe what we could do is to so in the ideal scenario you would, so the worst case, so why is this important? Because this is why like numerical linear algebra is cool, because you can just take like crayons and then like fill out a square matrix, and then if it's a cool looking pattern, then there's probably a specialized algorithm for it. Specialized algorithms means you don't have to use as much memory, which means that you can do way more calculations and more efficient algorithms. So if you see bottom line is, if your matrix looks like it's a very symmetrical looking pattern in some way, you can probably speed it up if you use the right kind of matrix. So we're kind of like going hunting for seeing what we need. Realize that all of these blank spaces are just zeros, so we don't need half the memory. And then if we're lucky enough that this is symmetrical, it might not be, but it might be. If this is also symmetrical on the anti-diagonal, there might be a way to just operate on operate on just like 1/4 of the total memory. And so operating on 1/4 of the total memory is going to be big savings, right? That's half the computations we don't have to do, right? And not storing it. Using special polynomials, all right? So, right, we declare this function. This is a bit funky for declaring the function with int64s. We don't need to like maybe using int32s or is like applicable, but so another note is that if you use int64s, you're just gonna own anyone who uses your code on a Raspberry Pi or like a lower end machine that doesn't have native int32s. So if possible, leave it at ints and let Julia figure it out. Maybe there's a more idiomatic way to make this function. And then the JSP function is just this function, calling the Jacobies on that 0 vector. So I actually don't like this function. So I don't like this function because it doesn't give you the power to, if you already define the vector before, to just apply that function in place. So that means that you modify the object, and so every time you call this function, it's creating that object again. It's calling this vn every time, and every time it will create that array of zeros. And it would be better if you had control over just like passing in data that you knew was not going to be initialized. Like maybe this is just like for an example, and then it's not a big deal. But you know, we're just trying to go ham here. We see this weird pattern again. I mean, this might be needed, but it might not be. It's unlikely that you need this big N all the way up to like 17. Yeah, 2 to the 17 is still like what? a million, not even. And then we get this nasty quotient with gamma functions, and then this declaration. I also don't like the spacing. I always put the spacing between the arguments. And then lastly, so this is where the line comes in, and this is why I want to do this, because it says uncommon for evaluate. Careful, it requires a lot of time to perform the calculations for j above 6, right? So we're gonna do a j. So the j. Start out with a j that's close to 8. That's 8. How about we try that with a j that is in 5, right? So that we can just iterate quickly, and then from a baseline, or let's try it with 6. 6, and then if we can get a baseline, and then we can see what we can do from there. Using series expansion. Oh no, we're there already, right? So this matrix looks super symmetrical here, right? Well, not along this diagonal, but along the anti-diagonal. So oh yeah, so this is another possible pitfall that I see. This function, or this filling, so this jsurf, this is a big expensive function, and then you're calling in this loop. Okay, oh, I think I skipped something. Oh lord, I skipped 2 of these. Oh yeah, so you have this function that's going to fill in your matrix. This person probably comes from MATLAB or from Python, likely, because they're just writing out their loops like it's nobody's business, right? You want this expensive function, you want this expensive procedure to be in a function, right? And this is why you need to read the tips. Avoid global variables, and then where is it? Put it in a function. Oh lord. Break functions into multiple definitions, right? So Julia's compiler works by specializing on functions and their inputs, very briefly. So if you don't do that, this is just going to be a bad time for your compiler, because there's no functions here, and so the compiler is just going to, like, Julia is not built for that. It will just run in Python mode, and Python mode is at least 100 times slower. So all right, where we have this jsurf function, and then we do this for loop, and then we try to fill it up with all this stuff. So I don't know of any numeric tricks to like speed up all of these computations, but for sure this function could use an inbounds. So an inbounds is every time you want to access an array, you have to check if you're inside of the if you're accessing something that's inside of the array and not outside. Otherwise, you segfault it or something. That's bad, because that's going to cost you a lot of performance. Getting rid of those bound checkings can also help you cut down on branches, which can have all sorts of beneficial knock-on effects. And so yeah, that's kind of the landscape. So big lessons. Let's do this. Big lessons. 1, avoid globals. 2, put stuff into functions. 3, functions. 3, split out in place methods where effective, / avoid allocations. 4, inbounds in tight loops. And then 5, and that's going to be the trickier one, is it's probably the one with the biggest payoff, actually. Use a special structured matrices. So that's where the biggest payoff is, but we're gonna see how this works out first. So let's see, do I even have all the so what else are we doing? We have revise. All right, now we're cooking with gas. Oh, what? Add revise. I don't have revise on this one, but we're gonna add it. Oh Lord. Let's check. Let's try doing this. Well. We're downloading a bunch of stuff. And then, ooh, I forgot probably one of the bigger ones, which is we're going to try and multi-thread that computation if at all possible. So, yeah, those are embarrassingly parallel tasks, right? So we can multi-thread that. Multi-thread that population. Might help. We might get a lot of cache contention if or false sharing if the function is not expensive enough. Oh dear Lord, why are you precompiling now? Also, let's tweet. These codes have some easy performance, some low-hanging performance opportunities. We're gonna try to pick them out live on stream right now. Come hang. Twitch.tv/brainrpg, and then boom, we're good to go. Oh Lord. Alright. Using, I guess the include, and then Jacoby, what is it? Yeah. Oh. What? What do you mean there's no? Oh, that's why. Then Jacoby, I need to fix that typo. G, change that case. Alright, don't change that case. Alright, using revise, and then we're going to include it. Jacoby. Oh, Lord. Wait, I forgot. Let's put in some timing statements. Vim, Jacoby. Right, so let's do this here. Info 1. Wait, oh Lord. 6. Multi-threading. Fill first matrix. Info. So second matrix. JSPFM. Oh, cute. They called like the. Alright, I get it. So the second matrix, and then lastly, info, fill third matrix. And they're already timed, so we have that. Gamma not defined. What do you mean gamma not defined? Oh. Using special functions. Probably that will help. Using special functions, and then using special polynomials not defined. Special functions, special polynomials. What? Where are those from? Special polynomials. Alright, so it seems that this Pluto just forgot there was a dependency somewhere in there. That's fine. And then we're going to write down our timings. I think I commented out. Probably, possibly, that's what I did. So we do using special polynomials. Where is it? In Jacobi. Using special polynomials. Extra token polynomials after another expression, and then we're gonna do the best trick. One, Control Q, bam, and we're jumping right where we're supposed to. Back, yeah, super cool. Eval Parse, how you doing, my man? We're performance tuning some codes. Yeah, you might have missed the announcement, or oh wow, this does take a long time. Error, no method matching, blah blah blah. Ooh. Well, that's no good. Jacobi, top level scope, 64. So I think this is 9, Control Q. How did this work? So let's try running that. Can I? Oh, I know what I should do. We're gonna do the good old one line at a time. Hello? And then we're gonna paste this into our buffer, and then we leave, and then booyakasha. Nope, not that one. Booyakasha. Nope, not that one. Let's try this again. 14, and then V that, and then go to the end, and then yank it again. Oh Lord. V there, and then that, yank. All right, should be fixed. And then, oh, why is it not working? God, I hate not. Paste. Why? Why do you do this? Oh, I know. I will just paste it here. Cat Jacoby. Copy paste that. Screw it. Oh, I can do this. Excel minus IB. How about I do... why can't I do this? So where did this go wrong? So after the first matrix, we're having some val issues. No method matching this val, so it wants that. Let's try and give it that, but with a val. Ok. Ah, ¿por qué no me dejas copy paste? O la vieja confiable. Notebooks, Twitter. Yeah, this is easier. Jacoby. Excel minus IB. Boom! Okay, that worked. It's good enough for me. What? Okay, so that's the first problem. Zeros. Okay, so does JSPFM exist? It's a 13 by 13 matrix. Cool. What in the... Alright, so maybe we can time that. Fill second matrix, no. Fill first matrix. Okay, this we can do. Time. And again. Okay, so and then Jacoby to hello. Hello, policia. There we go. Oh. A ver. What? There we go. What's the difference between time and timed? See, this is slow. This is slow as hell, right? You're doing like 12,000 allocations. You should only be doing like as many as, so if you were to do an in-place method, you just have like this square matrix, and then you gotta fill out like, this is like a banded matrix probably. This is a square within that. Maybe? We'll see what it looks like. But the point is, this is taking like milliseconds, and it should not be taking milliseconds. It should be taking, I don't know, microseconds. It's only like 17 of these. We'll see. But the point is, the first one takes 0.004, 2, and so that this is unacceptable. On our Julian pride, 0.0042, and then 12k allocations, and then I guess we should call this seconds, right? So we need to start doing, first things first, we got to measure it. Then we do timed, and then I think this one is till third matrix, no, till second matrix, yes. This is the one that's broken. Okay, so we'll come back to you. Third matrix is, yeah, third matrix. There we go. See, this is closer to what we hoped for. 35 allocations, yeah, because that's 17 plus 17 times 2 plus 1. It's coming in, and then that's it. That's all it needs to do. Still looks hella slow though. Alright, so third matrix is 0.0067 and 35 allocations. So let's just do it at the top. Uh, 0.667 and then 35 allocations. And then how many zeros was it? 1, 2, 3, 4 zeros. Okay. So and then the last one, oh, this is first mat. No, that's the third mat. First mat, da-da-da, and then the second mat. Second mat is the other one. So first we need to fix the bug. We love the fixing bugs. That's not the problem. Second matrix. What? So it works? What? It does not. So this is kind of weird. I'm gonna look at this Pluto again, because this Pluto does not to me seem. Did it have any mistakes? Yes, it did. Yes, you did. Sneaky, sneaky. So we ignored that there was just a bug here, which is bad. People would call this bad. So let's just try JSPF 1, 2. Alright, so how is JSPF defined? And that's because of the bigs, probably. So if you don't know how to do this, you're like, oh no, what could possibly be going on here? And then if you've got your revise, if you've done using revise, then you can just do edit, and then you can just skip straight into the function. And so this is where we're going to patch it up. So first of all, I kind of hate not using this the shorter version, if it's just one line. Let's actually, that might help us, because it's just like one big product. So why don't we just do that? A is equal to this. I know it's not true. I know I don't need it, but I might as well just use it. And then V is equal to that. Yep. And then V is equal to that. Oh. And then, so we're going to do A times B, and then divided by wait, let's do C times that, and then D. Yeah. Alright, let's go from here to rainbow bracket. Wait. Let's go to the end here. V to the... Oh, it's the square root of this entire thing. Alright. Let's do that then. So the algebraic version of this is there's some 2 to the something here times square root of foo, and then this foo, right, and then that's the times bar times JSP bar. Yep. All right, good. And so this is 2 to the what? Yeah, 2 to the float 64, and this is just weird. I'm breaking this up so that maybe it's a bit clearer what I can poke around with. B is equal to change in parentheses, and then change in parentheses, again, change in parentheses, again. Oh, there we go. B, and then the JSP. Cool. And then we got A times that. Cool. Let me quickly check something. Checking that the Slack is on fine. Slack seems fine. Alright. So the big warning signs for me are this float thingy going on, and then the bigs. Just give me a second. Correct. So we're gonna try and run this without the bigs. We're gonna assume that gamma is smart enough to figure out that if it needs to be bigger, it will convert to a bigger int. Otherwise, we're just gonna cry. And then we're gonna hope that it works. So the magic is hopefully that revise automatically like loaded the code that we just modified, so we don't need to restart Julia or reread the file. So that did not help that much. Maybe. Method, no method matching, blah, 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 blah. Where int? Ah, I see. We might be calling it with a float. And that would be problematic. Why are we calling it with a val? Where's the val come from? Alright. Let's pull out the big guns. So this is Julia, one of the standard Julia debuggers. It's going to take a while to compile this function, but we're going to get there. Oh, hello. Oh, lordy. Why is it doing this? What did you do? Okay. Yes, so we know how to freaking... Oh. Alright, chat. What do you think is the 2 to the 17? Is it bigger than the type we have? No way. Is it close to a million? Not close. So we're just gonna get rid of this. 2 to the n. We're gonna assume that n is an integer. Q, 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 Q. Type var. So what are we calling this JSP in? So JSP with 4 arguments is what's causing a ruckus here. JSP 1111, and then that works. Does this work? That does work. So what's the problem, bruh? Oh Lord, don't tell me that we're passing in J from the global. No, bro. Can't do that. Can't do that. Oh. Well, it's a const now. But where is it coming from? What's this JSP? Alpha, beta. This is a mess, man. Ow. K1, K0. Edit. Enter JSPF 1, 2. Why is it doing that? Okay, I think I need to check the help commands here. BP add. What's my frame? Okay. L toggle. What? Debugger's bugged. So let's try U3, U4, U4, U6. Why am I seeing this weird interpreter mode? Hey Lemonade, which tweet is this from? Let me show you. This is the tweet. Oh Lord. Brain RPG. I don't have the Chatterino up. Oh, I might. Chatterino.com. Let me see if it's running. No, give me a second. Chatterino. Chatterino. I should be able to post this. Why is it not posting? Have I given myself like rights to post? I don't think it does. I think it detected that it's like an image. I needed to... let's try a link. If you go to my Twitter, so it's twitter.com/that one, then I've just retweeted myself doing that. Alright, so for some reason I can't see my own darn comments in the chat, but I can see y'all. Alright, and I think I don't need this anymore. Why is this debugger not running? U6, U7, U8, U8, U gamma, U13, U. Oh, there's still bigs here. Oh, this is weird. So if I do gamma 3, yeah. What? What? We're gonna try. I'm gonna get rid of this. We're just gonna get rid of it. Second matrix. Oh, I might have been feeding in bad inputs then. Cool, Lemonade. Yeah, welcome. Haven't seen you before. What brings you? What? Alright, yeah, we're good. we're good. That, and yeah, how'd you hear about the stream? Or maybe I know you from somewhere else and this isn't your, I don't know, this screen name of yours? Okay, let's just screw it. Jacoby. Missing comma. 1 control Q, bam. That might explain. That's why Revise didn't track it. Domain errors cannot raise into the negative power. JSPF, Jacoby, so 4. This is the one. So instead of doing the ugly hack, so tips 4, we're going to write this. So this is another tip that beginners struggle with. Tips for next time. And then we're going to do this ugly thing, float 64, and just call it like this, 2 to the n. So 2.0 to the n, and then that's more than enough for Julia to like figure it out. And I'm pretty sure I have to do this somewhere else. Add spaces to clarify. Invalid syntax. Oh, yeah, because otherwise Julia doesn't know if it's broadcasting or not. So those zeros add clarity. Oh Lord, this thing is still so ugly here. Oh, you came from the Slack. Oh, great to have you then, Lemonade. Glad you could join us. Is it evening, afternoon for you, wherever you are in the world? What can you tell us about yourself? What are your interests in Julia Land? So I'm assuming that the people who wrote the gamma function are very smart and that they will handle overflows as needed. And I think that's a fair call given the people that I likely wrote the wrappers for those functions. But we're still risking it. We're still risking it. Gamma, gamma, gamma. We're fine with a little risk though. Morning, it's the morning. Oh Lord, it's 9 p.m. over 9:30 p.m. over here. So, do you know this trick, Lemonade? So whenever you get a horrible stack trace like this, and you have Revise open, you just do 1, and then you do Control Q. So you see how 1 is the stack trace, the error related to the error in line 31. If you type in the number that's in the brackets, you do 1, Control Q, and then you're right where the mistake happened. And so there is likely some parentheses I just skipped out on. Which one is it? So not that one. Not that one. Not that one. Oh, where's this one? It's here. That's why you copy paste before you delete, right? Yeah, otherwise, I've learned that mistake before. Always like copy the line you're gonna edit for performance and then like just put it in a comment. Add space to clarify. So we're gonna do the same trick. 1, Control Q, and then this is gonna be the O. Yep. Oh, okay, we're back where we started then. An expression starting in Jacoby. 9. So we're going to do 9, Control Q. So we're back to the JSPF shenanigans. So I think we're gonna do JSPF. Enter JSPF 1, 2. Okay, now we can skip properly. Dear Lord. Why is this happening? Why am I jumping into like this weird format I'm not familiar with? Why is all my syntax gone? One, two, three, and it's done. I don't want that. One, two, step. There we go. So it's doing main JSP. So let's add a breakpoint at line 20 so that it knows not to keep going. Oh dear Lord. These stack traces get so mangled with generated functions. So it's not, so if I do 1, 1, 1, 1, 1, that works. That's not what's happening. It's in the quote node. So what's with this quote node? Oh, I don't think I like this design. Is it? Let's break this down even further. So this is trivial for the compiler to figure out that these, like all of these assignments can just be like folded into each other, but it's much nicer for the debugger to do that. So JSPF 1, 2, all right, still breaking up. Base square root. Okay, we're breaking up at the square root. Okay, now we're cooking with gas. See, so now we can see that it's in this square root. Let's do it again. B1 equals B1 is equal to this. Nope, the other one. B2 is equal to that. And then B is B1 is B1 over B2. Hello, frog on the shore. Frog on the shore. Where are you joining us from? How do you get my Vim to look all fancy? It is not likely to be that fancy. You can check it out on my config startup files. Startup config. So it's literally here. Can you see that link? Let me know. I just posted it in chat. You should be able to see my config files. And my .vims are there. I don't know if those are the current ones though. Yeah, those are, it might not be updated, but it's my .vimrc. It's basically just Vim with Nightline or Lightline or whatever. And then, what am I doing? Let me say, let's do the edit. Oh Lord. Edit. Oh, I don't even have the set highlight. Oh Lord, I don't know what I did. There's something, Vim highlight line. How do I do that? Highlight line. I love having that, and I don't have it right now. So, oh, I see. It's, set cursor line. Oh yeah, now we're cooking with gas. I love having this. So what I do? I did this. Actually, I kind of prefer this way to do the calculation. It's a bit neater for my eyes. That's beside the point. So yeah, welcome Frog on the show. How'd you hear about the stream? JSPF2, JSPF2, JSPF2 still bailing on me. Jacobi in 64. Could be an error with them. Unlikely. Let's try that. Base dot square root of 4. I only see frog. I only see from star star star. I have no idea what that means. I might have a profanity filter that flags something. Yeah, that's unlikely. Let's try and coerce this argument. Let's see. Oh, why don't we try this? B info. Poor man's debugger. JSPF2. Okay, that's not even being called though. Ooh. Or it wasn't. What? So let's do this. JuliaLang.live. Oh no way, it's working. Oh, great. Were you were just randomly browsing for people and I popped up, or do you have like some notification set up? Because I just registered like this week, so it's interesting to hear that you're the first person to come from there. So welcome aboard. Okay. Okay, so I'm not calling that. This is what I've learned. Whenever I'm like clearly not calling what I want to be calling, it's probably a good idea to like quit the session because you probably polluted some of your methods, and it's just easier to which. All right, so let's do that. Which? Why are you doing this? You are on the live. You check periodically. Oh. That's interesting. Well, I'm glad you came along. Oh, so we'll need to do using revise because we're on master. If you don't know how to get your Julia version, you can get version info, and then you can see that I'm on 1.6. So that means that certain things are broken, kind of like revise, or I don't know if it is, but the point is that the startup script for my revise is not working properly. Include Jacobi, tap complete, and then see, now it's working, which is fine. It just, I don't know, we were just calling in some method that we weren't supposed to. And alright, so that's a lot of infos. And if we call it again, it should be a bit faster. And then we'll see if it finishes. Yeah, so this big, oh no. Where did you go wrong, bro? No method matching this Jacobi ain't 64. So we're like halfway through. Bruh. Surprises in debugging land. So if we do JSP 1.2, ugh. There we go. So the problem is not when I call it there. The problem is when I call it here. So if we do, how about we just check the inputs? Info lm, and then, so if you don't know about these amazing debugging techniques, right? Just print statements everywhere. I like info. It's just a little bit more colorful. Whoop. All right, that was faster. So where's my M and my J? There's supposed to be an L and an M. Where'd you go? All right, let's get them. JSP, JSPF, blah 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 blah, JSPF, blah 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 blah. LM. So L and then L, info M, M, and then we can get the actual inputs that are causing us the headaches. There we go. So if we call JSPF, is it JSPF? JSPF, yeah, JSPF with LM 1 minus 6. JSPF with 1 minus 6. Everything goes to trash. But if we do it with 6 and 0, it's fine. Alright, so we found out that our boy Alejandro is not being careful with his inputs. So some about this you gotta check out, bruh. This is let's try the doc string here. There's a warning. Breaks for n equals to 0, q equals to minus 6. So you gotta check that out, man. Alright. And therefore we no longer care about you. And I guess, yeah, so everyone got to see some riveting live debugging. So if we just include it, 108, 108, where am I missing this? Oh, cool. Square root, where does it end? It doesn't end here for sure. It ends here. Boom, see? Alright, it's not too if we just skip out on all the bad values, it's not too bad. Alright, but still, we can do some fun stuff. Let's see what we can do. So this function, this should be a function. We can call this we can call it some like init j hype m, and then we do it with dim j, and then that we just do some like function. Alright, so m is equal to zeros, float 64. We could just leave it at floats. We'll do float 64. So it could be different. Dim. And then this is where we do our funky stuff. Inbounds for L in minus J. Oh, thanks for the clap, frog. And then M in minus J to J. We just do the M equals M from L plus J plus 1, M plus J plus 1 equals 1, J, H hyper functions. And then these names are not optimal. Let's say that kindly. I would not choose to have those. So what this function does is it does the same as this, but if you do it inside a function, it's way faster. You'll see how. So this timing this let's see, init include Jacobi init, and then the dims were the j's are j, and then the dims are, I don't know, 17 by 17, and it's not going to be negative. All right, screw that. 6, 4. Oh Lord, what is it? L&M. Oh, I'm an idiot. I should call this res. I always call it res. Whoa! Sec fault. Alright, I'm an idiot. I did not label my axes properly. Ooh. Silly me. Okay. Vim, Jacobi. Yeah, so how come this did not work? We're going to call it empty because we're just using the global constants anyway. So n dim, so init What's wrong with you? Awesome. Nance. And we get what we sort of wanted. In a sense. So we should do using linear algebra, and then we should ask upper triangular right, and that's the one. So we should do edit. So this matrix should be an upper triangular of dim. So can I just do upper, how do I do this? Upper triangular, so upper triangular. Yeah, I guess if I just use the view, there shouldn't be much of a problem. And then Julia will know to like get rid of that memory. We'll see. Wait. Let's try this. Beep, boop, boom. Let's not. I think the inbound should be the last one. Jacobi. Upper triangular not defined, cause I'm boo-boo. Jacobi. Alright, so it is upper triangular. But we're not being able to. Let's hold on this idea for now. We'll get to it later. Alright, this is the second split. I would want to add a function here that's JSP in place, and then for the convention of in place function we add the bang and alpha, beta, z, and then that's special polynomials dot Jacobi alpha, beta, vector okay. That should be cooler. What is this JSP thing? This JSP was I don't even know what the JSP is. So this is the one that looks legit. This is one that we can do inbounds on, and then this is another one. All right, so so we're just gonna call it JSR fem matrix, and then J equals J. No, we'll just do that. So we have include Jacobi JSR fem these square brackets for indexing an array. What did I do? Okay, so that works. Let's see. Right, so this is pretty fast. We're doing the last thing in the calculation. It should not be taking too long. Okay, but still, this is 170 allocations, right? So this is way too many, if at all possible. Allocated GSR F matrix. Alright, whatever that means. So where to go? JSRF. So JSRF doesn't look like we can improve upon it much. Sounds like a gamma function problem to me. But we might be able to do this. Whoop. I don't know, I think this looks like sometimes you hit the garbage collector and sometimes you don't. Still looks like a lot of freaking allocations to me. Inbounds, inline. So probably the good speed ups would be from trying to do some greatest common denominator no, you can't, because this is within the square root. Maybe there's some identities that you can use to like factorize some of those. But this JSR binomial here, binomial there. We like spaces. Especially for horrible calculations like these. Okay, could this be like, can you find the square of it first? How'd that help? It might, I just don't know how, or I don't see how right now. If I find the square of it, don't know that it helps. It could, I just don't know. What about this binomial? Don't I know that this is like, I don't know, this is some don't worry about it. We're still we are very much just throwing darts and seeing what sticks. So instead of doing this division, we can probably do this. It's probably the best floating point trick I can offer right now. But the compiler could probably figure that out as well. Fill the second matrix. Maybe this J only works if maybe the code only works if we go above J equals 6. Let's try it with 8. Bravely try an 8. Um, 3.5. Avoid big ints if possible. Tips for next time. Yeah, you don't need to do that. What else? Inbounds were appropriate. We need to figure out the... So we avoided the globals. Check. Check out the flag. Why can't I get emojis? I really need to crank out this Vim to be able to handle emojis, otherwise life is sad. Put your code into functions. We've done that. Yay. Split out in-place methods were effective. Avoid allocations. So this init, we should try this init one. init. Oh no, I should at least be consistent. Call it times begin. Then this. Why did I not like this? I did not like this. Ooh, let's check if we can do something like this. I for I in 1 through 3, and then 1. Too bad. Surf, J must K, J that. Wait, does the gamma function, does the JSurf function allocate anyways? Time JSurf 1 3 1 2. Let's call it me. J. Yeah, so that's one allocation. It can't do anything more than that, or anything less than that. Or does it? Can it avoid it? JSurf. It's maybe in the JSur. Yeah, so this is why. The JSur. So this is the JSur that like starts out, and then this is the JSur that we're gonna do this. JSur, and then we're gonna do VN alpha beta Z, and then we're gonna do function, and then in bounds for k in 0 to n. And now we're going to steal this, and then just end. And that way we can use a JSurf. So we can try a JSurf that has the V, the N, and the Q. And then that thing is just that with that. But JSur, and then right. And then this becomes like that. Okay, so JSurf matrix creates that. And then function JSurf matrix only takes in the V, and then does inbounds. So we basically have like a parallel chain coding, and it returns the V, and then JSurf VLM, and then JSurf matrix. Yeah, that's the JSurf matrix, and then the JSurf, and then the JSurf blah, and then the JSer, and then the JSer blah, and I just need my matrix. A ver, JSPFM, V, for L in minus J to J, for M in minus J to J, JSP V, plus J plus 1, M plus J plus 1 is equal to JSPF LM JSPF. Okay, so it's enough for JSPF. JSPF only. Yeah, JSPF does not need the bang. JSPF though needs an initial function. Okay, so we can start this thing with V, then JSP, then JSPF M on that V, and then JSer, no, then JSerf, and then so what do I need to do to time this? I only need to time JSF matrix. Okay, let's do the timed begin. Let's do that. Let's time it. Time. Da, 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 da. Okay, let's try this again. Alright, so we're still getting this amazingly fun error that I don't know where it came from. We're just gonna ignore it then. Oh, no, 12, Control Q. Jump! Jump, jump, jump. No. 9. Control Q. Don't worry then. Okay. So this third matrix is still pretty bad. Okay. So what we're gonna do now is to Oh my god, I forgot something else completely. Oh no no no. I forgot to look for this. Alright gang, what do you see? This is a big no-no in Julia land. What do you see? The fastest changing index. Oh my god, this is horrible. No, this conflicts with the global J. Bad, 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 bad. Yeah, this is bad. Yeah, that's right, Frog. Bad stuff. And then the second thing is, this is a matrix, and then the fastest index is scrolling over the M. So that's the rows. And that is no bueno, because Julia is column major. Ah, so we need to swap these. Tips for next time. Julia is, that's a big, Julia is column major. Here, we're gonna see. So, little experiment, alright? So that failed, but it's all good. So the first one is, or rather, let's fix that up. Down, down. Yeah, let's just get this thing where it's supposed to. So let's try this. This is a classic case of, but that looks like it's local scope. Yeah, so I think it's doing the right thing, but still, like having the names clash between like using the so here's the critique. These indices are clashing with oh no, they're not clashing. Oh yeah, these are the end ranges, and so this doesn't move. Okay, it might not actually be that bad, but there is something really bad that this is not. That's why I always uppercase global vars. Yeah, that's a good call. Or better yet, is to not have global vars at all. But the big drawback here is that these are, so Julia's column major, so it means that all the elements in the same column are like, if you're using like a rectangular simple matrix of floats or ints, they have a stride of 1, so that the next element in the column is the one that is contiguous in memory. They're all like nicely lined up together. And if you do this sort of access, then you're going to be accessing it by rows. So you're going across. So every time you're, like if the matrix is big enough, you're just like destroying the cache lines every time. And so you're just going to own your cache lines. So we're going to do this little experiment here. And we're going to time it. So, what's it called? J hype, these are? J hype matrix. That's 1, and then that's 2. Alright, and they should give the same value. Alright, so that's 1, that's 2. And then we're going to do a time for this, and that's going to be, I don't know, single allocation, and then, because I can talk about why that's a single allocation. Boom. One of these, so actually, wait. B time. So B time is like a fancier version of time, and it's the one that you should do for like more rigorous benchmarking. Oh, I'm an idiot. I just selected the same one twice. So that's What? Well, this is weird. I don't believe it. There's no way. My whole point about this was it's important for you to access Julia in a column. So the point is the index that is going over the column should be the one that like loops fastest. And it's in this case the M is going faster. It's the one that's iterating more quickly over the matrix. And this one's going across rows. So I'm not sure why there's not that much of a difference. What? Maybe we're just... Is it small enough that it doesn't get like owned by the cache? All right, let's just make sure that we're not doing the same in the final ones. So in the final ones we are doing it. Let's try that one then. Try this. Let's try that. Just whoops. Include. Yeah, so one of them is always gonna what? Not always. Alright, let's be rigorous, otherwise I'm just clearly oh Lord. Okay. Ugh. It's barely faster. Barely. Why is it not that much of a difference? Oh, okay, I'm pretty surprised then. Another one. Ugh. Alright, let's at least try to do an in-place method instead of a... What was JSPF? JSPF is fine. Ah, no. This function is horrible. Something about this is just bad workflow. Let's try this. GSP maker. A, B, C, D, no sé qué. And then you throw out special polynomials. Jacobi. And then what is it? AB. Yeah. So I'm not calling the constructor every time that okay. So JSP maker 2, 3. Okay. chat. I'm about to give up. Yeah, there's some quantum mechanics stuff in there. I don't know specifically what it is. Jacobi functions used to represent the eigenfunctions of the discrete and finite harmonic oscillator. Yeah, it's by a 2016 paper by Stefan Wyman et al. Here, let me post this again. Alright, I'm about to go to sleep because this is do J I and then end. I think this is the entirety of my lessons. Tips for next time. Multi-thread heavy loops. Tips for next time. Yeah, the Pluto notebook is pretty fire, not gonna lie. This code is quite a bit too hairy for me to like dig in just like out of the blue. I would probably rewrite this from scratch to not use any globals. That was brave not to try and do that. But let's see. Kind of runs now. I mean, that second loop is just, I don't know why it's broken, but we'll do what we can. Alright, we're gonna write out our finishing tweet and then call it a night. And put on a gist. Yep. Right. Gist description. Also, create a public gist. Alright. Let's try this again. Alright. Brain was pooped for this. Oh, Polytamus, how are you? Polytamus? Yeah, it's. I hope you mean the title, because I've never changed the title. I don't know. I really need to figure out a way to do it in an easier way than like logging into Twitch and then changing the stream title, because I never remember to. I just like clicked start streaming. But yeah, we need the live split. We have been running timings though, so I think that sort of helps. Entire code base to actually get some good measurements. Might come back to it tomorrow. For now, this is what I got. And then that's the gist. And then my takeaways are this. I didn't know Jake Gylenhaal knew Julia. It's actually Gylenhaal. Nice to meet you, Dan and Beard. I have got that before. But yeah, it's a pretty good day when someone tells you look like Gylenhaal, or however you say it. Streamlab Ops fork has tighter Twitch integration for setting titles, but then using janky fork of I don't know. I think I just need to be a bit more yeah, I don't know if I know you from Julia Slack, Dan. No, yeah, Jake Gyllenhaal is the guy from American Beauty. I used to look like him a lot. Yeah, Donnie Darko, that's the one. One time I saw Donnie Darko and I kind of tripped out because I thought I was him. I have pictures as a teenager where I am identical to Donnie Darko, and it's kind of creepy. Oh, if there was only a line, that would be useful. Yeah. Change the title midstream. So general perf tips at the top of the file are here. Whoops. We're gonna write those big lessons. So we're drafting a tweet. Maybe I should put the tweet here so that other people can see it. Oh Lord. We're drafting a tweet. No, don't discard it. Inbounds in tight loops, and then yeah, we're gonna come back to this tomorrow and then like refactor the entire code base. Cause some of that stuff is just not pretty. Not pretty. But it's fine. It's hard to learn how to code in a performant fashion, and I'm nowhere near close to my peak power. Oh cool, actors can get pulled into Julia Morass. Excellent. Oh yeah. Oh dear Lord, please don't. I hope there's nobody called Inbounds. That would be unfortunate. At BTime, just get their notifications owned on Twitter if Julia becomes a thing. Oh, I just got a nasty idea. Make sure they are test first. Test it first. Alright, and then the last of the big lessons. Use structured matrices. Inbounds has 5 followers and hasn't tweeted since. Yeah, I need to reclaim that account. Somebody reclaim that account. Ah, dear Lord, I can't edit tweets for. Why is there not an easier way to? I probably could have used that carbon thing that cool kids use, but I just didn't remember to, and now I'm stuck with this, so Ah! Oh lord. This is still way too many characters. Alright, screw it. Well, yeah, the hope would be that, yeah, exactly, Polytimus, that you can use some of the structured matrices to like actually do the calculations in a smarter way, or you're just not allocating as much memory ab initio. So that's just a bit smarter. Hey, Dan and Beard, where are you joining us from? Where'd you see the tweet from, or how'd you catch the stream? Do you know it's from Slack? Do you know it's from the Zulip or the Gylenhaal.live? And there we go. Tips for next time. And then let's do performance. Welcome to la la la. Performance tips, Julia. Yep, that's the one. That's the one. All right. We're tweeting. Oh no, we gotta add our ends here. Can't let people catch us like that. Dangling and for loops. All right. Well, that's it for me for today. Otherwise, I'm just rewriting this code from scratch tomorrow, if at all. And yeah, just not redoing this. Hi Miguel, it's Alejandro. It's amazing what you can do. Thanks for the tips. Although performance wasn't my goal, now I know what good practice looks like. Let's go on. Jacobian special functions is amazingly weird. Starting in the source paper, they based the method to obtain the function. Alejandro, qué gusto que estás por acá y mucho gusto. So I'm almost willing to bet that that function is funky because it's a generated function. And so you need to treat it, you need to be a bit more careful of when you're using those functions so that you don't, or it depends how they set up the interface. So I think the best practice is to define first, like make a constructor for it. So for example, this JSP maker that I have, JSP maker 1, 2, 2, 3, right? So that's a Jacobi whatever. So what you would want to do maybe is you call an f, right? And then this f, we needed a vector, right? So the vector was, I don't know, 0 for I and 1 to 10, whatever. And then the f gets applied to the, oh wow. The f gets applied to the vector, and then that gets applied again to, so let's say that g equals f applied to the v, so then the v gets applied to, it got applied to z, I think. Yeah. So this was applied to scalars. Okay, so maybe this function is not too interesting. But the point is, when you're dealing with generated functions, the interface might be a bit friendlier if you like define functions first on like the constructors, and then you just apply the function at the end. That's also going to be like easier for like hunting down the error messages, and because generator functions are famous for mangling any and all error stack traces, and that's because of what they mean. So Alejandro, I don't know if you actually know what generator functions are. If you don't know, I made a post about it. Let me see. How can I share this freaking post? So I actually made a repo because I didn't know what generated functions were, and they're quite a bit, they're quite tricky. So here's what I recommend. Here is a case of a repo I did, and the best way to understand it is to check out this presentation by, I would say, Stefan Karpinski, right? So he explains why generated functions are really, really cool in Julia, but 99% of the time you don't need them. Basically, when it comes to special functions, are a great application of generated functions for the following reasons. You want to specialize very, very, very heavy numerical code based on some information that's independent of the data. So 99% of the time, don't use generated functions. If you have to think of a way of encoding some parts of your algorithm into the types. So that's what's cool about generated functions. If you can encode very specific information about your algorithm into the types, and that allows you to super specialize the algorithm, to super boost it, then it's very much worth it. Otherwise, it's unlikely to be a good trade-off. Don't take my word for it. Take it from here. If you are very much it is a tricky subject. If you're a beginner, you probably just, I'm saying this because we're talking about generated functions, but like I would not talk about generated function with beginners for like, I don't know, 2 months of them like coding into Julia like every day, unless they really wanted to. So JuliaCon, Steven Johnson, meta programming, right? And it's not just me. It's like one of the guys who's like consistently writing Julia codes that beats Fortran. Is this guy, Stephen G. Johnson, who's like an absolute beast. He wrote the fast Fourier transform implementation that gets used like almost everywhere. And so in this presentation, Stephen Johnson will say, the tips for next time. Probably forgot. Before you get into all the meta programming haziness, no, what is it called? Brouhaha. Please watch this video where Stephen Johnson, I don't know what his G is for, Stephen G. Johnson lets you know why 99% of the time it's not, let's exit here, the best idea to reach for a generated function. Right? So yeah, it's unfortunate that you have to deal with that, but the trade-off is if there's some very, very, very particular speed-ups for your algorithm that you can get with generated functions, then it's worth it. In particular, special functions are very amenable to that sort of stage programming, where like maybe if you know that alpha happens to be 1, then you can special case all of those gamma functions for a particular type of reduction, and then that will cut down a lot on the floating point divisions further down the line. So you want to specialize on each of those cases, but you don't want to build them out by hand before your algorithm. You want to have a recipe that gives you the proper algorithm. And so generated functions are a way to like make a recipe maker, and so whenever you call the recipe maker, it will give you the proper recipe, and then that's your good algorithm. So that's why you're jumping in between like these functions. Yeah, generated functions are like compile time copy paste, if that makes sense. Rather, that's more metaprogramming. Metaprogramming is compile time copy pasted code, if that makes any sense. And yeah, compile time doesn't really make sense in Julia because it's like you can go back and forth, Like it's not well defined. Like from one point onwards, it's just never compiled again. It's more like whenever a method needs to be specialized, then compilation happens. So it's not. This is show. And so generator functions are a type of metaprogramming where you can specialize your code based on the types of the functions themselves. Oh, I tweeted out the link, but you should check out this. Oh no, that's not the name. That's not the name at all. Check out the. If you any of the previous links that I've posted in the chat are pretty amenable to explaining this, because there's also one called Stage Programming by Jeff and Stefan that's actually really cool. I enjoy it. Jeff, Bezanson, Stefan. I can how they define it. Yeah. So Alejandro, so here's the truth of it. This is what I had to do. I had to take 2 blog posts one by Steven Johnson and one by Jiahao Chen that talked about generated functions. This is let me show you. I might have one in my blog, and it doesn't really work. My blog's not really online yet. Wait, let's show chat our blog. The blog. All right, we're about to go home anyway. So this is the blog. It sucks for now. We're getting there. And in the blog, we have a hidden link. Nope, not that blog. In this link. No. This the one. In this link, you can. Oh no, where did Chatterino go? Chatterino. There's Chatterino. This is my blog post. Well, so that's a blog post that's based on something Steven Johnson did. Alejandro, you might very much enjoy this because you're doing something specifically to special functions. So it goes through an example of it. Why is the copy button not working? Shame. At any rate, it talks about a very specific case of generator functions and how they're very useful for numerically intensive codes with regards to elliptic curve integrals, right? So the whole point is, if you can talk about a very special, like, if there's a very specific speed up that you can get that's independent of the data, and you can, so there's certain characteristics about your problem, like sometimes your algorithm will have to go longer because you just got in more data, but sometimes your algorithm can be special case for certain elements that are independent of the data. And in the case of this blog post, it has to do with the types of the integrals. Certain types of integrals you can know analytically with, depending on the powers, very, very specific analytic solutions. And so those are 50 times, gajillions of times faster than having to solve a quadrature or integrating yourself by hand. So if you can special case that knowledge into the types and then build a function that can get you those results, that's going to be worth it, no? So obviously Steven Johnson built this based on a paper by Homer Reed. I haven't read the paper entirely, I've only glanced over it. And I didn't get the point of generator functions. And so I looked into it and I found this really cool blog post by Steven Johnson, and it was only based on Julia 0.7, and so I updated it to Julia 1.0, or at least I think I did. So if you find any typos on it, please let me know. And that's one of them. And then the other one is the presentation that I just posted in chat about Savitsky-Golay filters and that one's explained by Stefan Karpinski, so go nuts with that one. But yeah, we should not be talking. I should not be talking about generated functions this frequently. It's just unlikely to be helpful to people. Like if you're dealing with special functions, then it's likely to be like useful to you, no? And it's part of the approx.fun ecosystem and how they use things, and that's why you ran into it with special functions.jl and stuff. But it's not that usual to run into this like in the wild. Like this is, you just like your niche our niche physics area just happens to like run into this head on, no? But yeah, you don't necessarily need to know about this. All right, anybody else got questions? I'm about to log off because what's going on? Pluto. Rip retinas, people. I'm sorry. But yeah, look at this structured matrix. Missing some context, but yeah, generated functions can't do everything. I can't find this I want to share, but the core docs describe it a bit more if you need info. Yeah. I was unhappy with the docs, so I rewrote this blog post, and it kind of helped me out. But I haven't read the docs in a while, so might not be. Let's just read the docs. Julia generated functions manual. Metaprogramming. Generator functions. Alright, just let me take my sip of water. A ver. A very special macro is @generated, which allows you to define so-called generator functions. These have the capability to generate specialized code depending on the types of their arguments, with more flexibility and or less code than can be achieved with multiple dispatch. So you can hyper-specialize code depending on the types, with more flexibility and or less code. While macros work with expressions at parse time and kind of access the types of their input. So this means that they can only look at the spelling of the code, like they only look at the squiggles, not the meaning of it. Does that make any sense? A generator function gets expanded at a time when the types of the arguments are known, but the function is not yet compiled. So it gets a bit tricky because you have to know like where in the Julia compilation pipeline things or how much information the compiler has, and then that's why the macro exists, so that they're like, oh wow, this moment in compilation time we can do a whole bunch of static analysis, and that will allow us to super specialize. Instead of performing some calculation or action, a generator function. So this is going to talk about the implementation, and that's a bit funky, no? And if you haven't looked at metaprogramming or handling expressions within Julia, that's going to get tricky because there's some special handling. Yeah, function ordering. The generator function declaration returns a quoted expression. So this is a big one, right? The quoted expression is a generator function doesn't actually, here, let me show you. Let me try and show you with my repo. Stage filters. Alright, so this is the code that I wrote based on the Stefan Karpinski talk, and it's basically somebody else's code, and I also remixed it. So if you've never looked at expressions in Julia, you can do it like this. Julia. Yada yada yada. Expression equals for I in 1 through m, and look at that. This is an expression. I can manipulate this. What's the arg? Like, what does this look like? Oh, it turns out this is like, if you've ever looked at abstract syntax trees, then this is like what the Julia representation of it. There's this symbol for, and then it has this, it's at the head, the symbol equals, and then it takes in the symbol I, and then there's the range, and this whole thing is a block, no? So the thing is that if you do, so x, if I do x.args, then I can access, right, x.args, right, I'm there, x.args1, and then what can I get here? The head, no, let's go into the args2, and then let's go into the args2 again, no, let's go into the args3, that's the one. So look at this, the expression here is, this is the expression, right? But I can access that element if I'm smart enough with manipulating the syntax tree with all of these accesses. But that also means that I can change it, right? I change that expression, like that this for loop block will now be from I1 to n and not 1 to m. Or I can make it, you know, from n to minus 1 or m minus 1. And so the expression has changed. It hasn't been evaluated, like the squiggles of the code itself. I'm just manipulating them. So the idea is, if you're smart about handling all of these for loops, like where they start or where they end, and you can maybe get an idea of it. By the way, you interpolate with let's say that m is 3. So x, yeah. If I wrote z equals for I in 1 through m, oh no. What? Oh. No. Okay, I'm failing. What? Okay, this is weird. For I equals that unexpected. Oh, I'm an idiot. End. Yeah, so you can interpolate with $, or you should be able to. There you go, right? So $, helps you interpolate. But the point is, I have this very specific setup for my algorithm that I can encode into the indices, into m and m, and because the for loop ranges depend on the m and m's, the rest of this is just me manipulating like all the for loops, like manually shoving in all of the index accesses that need to happen in that tight loop, so that at the end of it I get the most amazing, handcrafted, perfectly optimized tight loop, and it's worth it in the end. But you don't get like a result at the end. You get an expression. So this is why there's a quote return. There's a quote return end, and then you have to do, you return an expression. So generated functions, you have to give them an expression, and then they get evaluated by the compiler, and all that magic stuff happens behind your back. So that's what this generated functions will tell you. And there's a couple of rules for how they can or can't be used, right? When generated function is called, the expression it returns is compiled and then runs. So this is the last expression. To make this efficient, the result is usually cached. And to make this inferable, only a limited subset of the language is usable, right? So you can't use everything within Julia, because you're at this funny place where the compiler has certain kinds of information and it's trying to work things out. Flexible way to move work from runtime to compile time at the expense of greater restrictions on allowed constructs. So you have to use the add generator function. You only have types. You don't have access to the values. So all of the manipulation I do here, all of it, it's all based on M and N and or stuff that I just cooked up for myself. I can't use any of the values within the data that I get. It has to be independent of the data, right? Then you don't calculate something, you manipulate an expression and you return an expression. Generator functions are only permitted to call functions that were defined before the definition of the generator function. Yeah, so in Julia you can sometimes do stuff like foo of x equals bar of x, and then bar of x is equal to 2x, and then you can call foo of 3, and that works in Julia. Yes, but they also come at a cost, and we're going to talk about the cost. Ahorita hablamos del costo, Alejandro. El costo es, debugging them is hell, and you'll see why. Because so if something wrong happens with my foo, if I do like nan, no? Foo of nan, then I could probably just say like, oh, if I do using the debugger, no, not the debugger, but I could probably do something like, oh, how did this lower, no? Foo, what happened to it? What were my types? Code, warn type, no? Okay, everything's working fine with inference, no? Code, what does LVM do? Oh, LVM does that, cool. Oh, what's the assembly? Oh, I can do this. No? What? Okay. Foo. Okay, so you have access to see like from where your function gets defined, how it gets translated down the compiler stack until like native code. But when it's a generated function, because it returns back an expression, debugging it is not nice because you lose, somebody can probably correct me, but you lose access to like the stack traces. They just get mangled along the way. Yeah, I agree with Thomas here. It's better to think of them as like you are willing, like you are trading mental, and you're trading a lot of mental complexity for this a generator of functions that can super specialize to particular cases, and it very much better be worth it. I highly recommend that you check out the function on the YouTube videos on generated programming, no? Because you get none of this. You don't get access to the debugger, you don't get access to the code warn type. That's why the error stack traces when you're using those functions, they're just not as good. For now, I don't know if it's a fundamental limitation of the approach that it can never work at all, but it's a tough problem, and there's smart people that have worked on it, and I don't know, some might be worked out. Oh yeah, and so one of the last things that we have to talk about here is that they cannot mutate or observe any non-constant global state. So input-output locks, non-local dictionaries, or using hash methods. You also can't use, what was it? This means they can only read global constants and kind of have any side effects. So they also have to be pure functions. Yeah, they have to be completely pure. There's an implementation limitation. There's also that they currently cannot define a closure or generator, right? So there's like all of these corner cases for them that you can't just like willy-nilly say like, oh yeah, like I'm just going to use a generator function here. It's like, no, you have to know exactly what it's for. No? It's a very, very specialized tool. It's very worth it where you can pull it off, but it's very, very specialized. Yeah, I don't. So polytomos, I don't know anything about error handling. So if you know, like, I just know that people care a lot about error handling, and Julia's like my first and kind of only programming language where I've like dealt with errors or with large enough code bases. So I don't know why it's so good or bad or like performant or not. Like I can't really compare. I just try to work things out and like monkey patch at the REPL. Note that the body returned a coded expression, namely this, rather than blah blah blah. From the cost perspective, this is identical to a regular function. In fact, you don't have to know. Oh, stringly typed. Oh, that's not good. So you would want to have like special, you'd want to be able to dispatch on the error type. Yeah, handle the error type, right? You want to say like, oh, this was like an array out of bounds when I was like deep in my kernel, or like, oh, this is like an out of memory error when I'm like doing I/O, or like, or when I'm going out to the server. You want try catch and Julia to actually use multiple dispatch on the error type. Okay. I'm very much not a language, programming language compiler engineer person, so beats me, but I can't tell if those proposals are worthy of merit or not. But if you know, if you're interested, they always welcome people writing a proposal and like actually taking on the some big interesting cases and see how the corner cases work out. Yeah, for sure. I mean, the best thing to do is to just write a package and see like how it works out. Yeah, see, you also have to be careful that it's not like called on every iteration of your hot loop. You want to initially just call it like a few times and then like run it um, against a bunch of data that it has to munch, and then the specialization was worth it. Mm. But yeah, Alejandro, if you're interested, this stage filters function is at least twice as fast as the SciPy function. At least. It should be, something's wrong with the benchmark. It needs to be, it used to be SIMDing, and it's no longer SIMDing, and I also need to parallelize it. But, you know, we'll see. Don't copy these examples. An advanced example, right? Pre-specialized function sounds very concrete. Yeah, I think by concrete you mean you're not reaching out to do any sort of mutable state, and it kind of has to, yeah. Otherwise, you can just you can also hit world age problems, but don't worry about that. Just code your normal Julia, and if it's slow, who cares? Oh, unless you're like making something that's mission critical, then you call in the big guns. Just get it working first and test it, and then you're good. But yeah, see, it's also worth it when you're doing like these incredibly interesting n-dimensional arrays manipulations where you really want to know like the dimension of the thing and have a very specialized method for it. That's where you're most likely to use them without even knowing about it, actually. But, you know, don't worry about it. Okay. It would be amazing to obtain the matrix with the constructors you're talking about. I'm interested in that. Alejandro, tengo una buena noticia. There's a tutorial in Julia Physics that is all about that. Collection of physics tutorials. So let me show you, because it's exactly what you need. Speeding up quantum mechanics, matrix types. You need to read this. Yeah, and or you need to check out courses on numerical linear algebra by Gilbert Strang, and I think the easiest one is computational methods for scientists, and engineers, Gilbert Strang. Computational science and engineering. Yeah, this is the one. So, este es un curso entero del MIT, en donde el jefazos Gilbert Strang te habla de todo esto. Gilbert Strang. Otherwise, there's a bunch of other courses by MIT that are a bit more current on numerical methods and specializing on and numerical linear algebra. Like just finding out that your matrix has a certain structure, then that's going to be very, very important. Pero cheque este tutorial. Porfa, avisa en el chat si abriste este de Speeding Up Quantum Mechanics, Matrix Types. Y pues, awesome, yeah. Yeah, using the Unicode plots is also way lighter. If you're going to be doing a lot of just checking out that the image is, that the matrix looks the way it should, try and use the SPY from Unicode plots. I'm going to write it in chat. Unicode plots.jl. ¿Sí? Y pues Alejandro, ya sabes, si tú o tu grupo del INAOE necesitan algún físico que les ayude a que corran más rápido sus calculitos, aquí andamos, A ver si un día no sale la cooperacha para proyecto, paper, beca, yo qué sé. The more people that use Julia in Mexico, for me, the better. ¿Sí? Alejandro, ¿pudiste entrar a este tutorial? Sale, vale, y ya sabes dónde encontrarme. Matrix Zoo, jail, GitHub. Matrix pencils, matrix pencil. Design structure matrix. OTPP. Quantum algorithms. Loop vectorization. No es eso. Matrix Depot. Matrix Depot, JL, GitHub. Sí, chécalo después. Frog on the Shore. If you're interested in any of this structured matrix stuff, this is probably a good, cool repo to check out. It's matrixdepot.jl, and let me show you the documentation because it's 50 times more eloquent to see the pictures than I can show you. Choo. Hello. Sorry, rip your retinas. Sorry. Alright, so these are all the possible functions that are in the matrix depot, and with any luck there's some very specialized methods for multiplying, getting the inverse, doing the singular value decomposition, getting the eigenvalues, blah 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 blah. So this is what they look like, and that's the special thing that they correspond to, and then so it's more like find your matrix, no? This is a Clement matrix, companion matrix. I have no idea what most of these are, but ding dong. Forsyth, Frank matrix. Yeah, pretty matrices for everybody. Gurkar, Hadamard, Hilbert matrix, inverse Hilbert, Invol, Kahan matrix, Lamer, Lotkin, magic matrix, Mini J. I'm looking for one that's like, yeah, if you want to look at pretty pictures, structured matrices is where it's at. All that pixelated goodness. Alright, people. Buenas noches. It's time for bed. Take care. Yeah, so Alejandro, all you do is linear algebra. Todo lo que hacemos es álgebra lineal. Eventualmente todo es álgebra lineal. Pues, and you gotta use the best algorithms that somebody else already wrote. Don't redo it. Somebody else has spent like a PhD specializing on the matrix type. Find the matrix type and then get Julia to solve it. Multiple dispatch, baby. Bueno, gente bonita, buenas noches. Bye bye. Un gusto.